So we're going to do another problem where we're finding the work done by all of the forces we can identify and then using that to find the total force, total work that's done, and check that to make sure it matches the change in kinetic energy. So here's what we've got. We've got an incline, a pushing force. We don't know what the force is, but we'll figure that out. An incline of a certain height. We know the mass, the angle. Let's say that the distance is, say, 4 meters, just so we have different numbers for everything. Okay, so the forces that we've got to work with, so we know the work done by each force, we have certainly mg, we have force normal, we have this pulling or pushing, this pulling force that's up the incline, and then because it's moving up the incline and there is friction, there's going to be a friction force. And so to set this up, the displacement is along the incline of 4 meters. Yeah, that's right, because this is 2 meters here. So that tells you if you use SOHCAHTOA, that gives you a distance of 4 meters. Okay, so we find that if we're finding the work done by the normal, that would be the normal force times the displacement times the cosine of 90 degrees. So that's 0 in this case because the normal is perpendicular to the displacement. For the work done by weight, we can do mg times the displacement times the angle between the displacement and the weight, which is a little tricky because the displacement is like this and the weight is like this. So you can actually find that angle, right? That would be 30 degrees here. So that would be 120 degrees. So you can do that, cosine of 120 degrees. Or you could calculate it as m times g times the displacement in the direction of the force, which would be just this 2 meters. So 2 meters, times the 2 meters, and that would be negative because the force is down, but the displacement is up. And so both of these are going to give you the same thing. A d times cosine of 120 is going to give you a 2 again. And so you can calculate this pretty quickly. The mass we've got is 0.2 kilograms, 9.8 meters per second squared, times then 2 meters. I'm going to use this value down here. That gives me 3.92, I think, joules, and that's a negative. Include that negative sign. So that's the work done by the weight. So we've got all of those even before we have any other information. Now we need to look at the work done by everything else. And so to find the friction, I think we can do this. The force of friction is mu times force normal. And the normal force is going to be, I think the only other force, if we do our force diagram, so let me set up our force diagram, I'll redraw that. We've got, if we set up this as our x and this is our y axis, then we've got the normal force, force normal up, we have mg pointing this angle. It's kind of a sloppy. This is our force friction. This is our force pull. It actually needs to be bigger than our force friction because we've got a component of our weight. Here's our weight. We've got the y component and we have the x component. And there's an acceleration, right? Because we go from 0 velocity to 3 meters a second. So this normal force is equal to the mgy, which is mg cosine of the angle. So this is equal to 0.2 times mg cosine of theta That's our friction force. So the work due to friction, work from friction, the displacement is up. It's in this direction. And the friction is down the incline. So this would be force of friction times the displacement of 4 meters negative. So this is also negative work. So this is minus 0.2 times 0.2 kilograms times 9.8 meters per second squared times cosine of 30 degrees times 4 meters. That's a lot of terms, but it's again just putting something into your calculator. Okay, so I wrote down the wrong value for mu. I had it confused with the mass, so that should be a 0.1 there, which I've had to change in the second equation. When I put this on the calculator, I get 0.68. So that's the work due to the kinetic friction. Okay, so here's what I've got so far. I've got work normal is equal to this. Work of mg of the weight is equal to this. Work of the friction is equal to this. And then the last force we need to find out is the work due to the pulling force. But if we want to, we can sort of cheat our way around that and realize that the work total is going to equal the change in kinetic energy. That is kinetic energy final minus kinetic energy initial, or 1/2 mv final squared minus 1/2 mv initial squared. And this total work is going to be work normal plus work of mg plus work friction plus work of this pull force. And so all of that is going to equal 1/2 mv final squared minus 1/2 mv initial squared. And if we look at this setup again, our initial speed is 0, our final speed is 3. So we can just put everything in. Our final speed here is 3 meters per second. That's 0. So we can say work normal, that's 0. This is equal to minus 3.96 joules. This is equal to minus 0.68 joules. This we don't know yet, but we're about to find it. And this mass is 0.2 kilograms. And then we gotta square that. So we get then minus, this is going to be about 4.6 is what it looks like, yeah. Plus work by the pulling force is equal to 1/2 times 0.2 kilograms times 9 meters squared, joules per second squared. And this has units of joules. That's going to be then a 0.9. I'm going to add this to both sides, plus 4.6 joules, so that cancels, plus 4.6 joules. So my work total for this looks like 5.4 joules. And then if I want to find my force, well, the work of the force pull is just looking at this. This force is in the direction of the displacement, so it's force pull times the displacement times d. That's 4 meters. This is 5.4, so FP is equal to about 1.4 newtons. Okay, so it's just the work done by each force, and then the total work done, we didn't actually have to find each individual force. Now you could have found this pulling force by saying, oh, I know the velocity, initial velocity, final velocity, I know the distance this has gone. Looking at this picture right here, I can find my acceleration. From my acceleration, I could find how big this pulling force has to be. So you could go at it a different direction and then from that find the work. But since we were going down this path, I figured it was a little faster to just do it like this. So this is the work done by the pulling force. So we have the work done by each of the individual pieces. Oh, and the total work is, of course, equal to this 0.9. This is the total work total, which is equal to 0.9 joules. And so that gets to all of our pieces, and you can see how these pieces hopefully add together to get a consistent answer. And you can check everything by going back and calculating your acceleration if you want to do the problem that way. That works as well, but I wanted to use what we were just learning to solve this problem.